Our modern world thrives on information. We communicate instantly across continents. We access vast stores of knowledge with a few keystrokes. We navigate our lives with powerful computers in our pockets. This digital revolution, in all its glory, owes its existence to tiny components called semiconductors. These microscopic marvels are the brains and nervous systems of our devices. They power everything from smartphones and laptops to cars, airplanes, and medical equipment. Understanding semiconductors is key to understanding the modern world. Semiconductors are materials with unique electrical properties. They are not perfect conductors like copper, nor are they perfect insulators like rubber. Instead, they occupy a fascinating middle ground, able to control the flow of electricity with remarkable precision. This controllability makes them ideal for creating the transistors and integrated circuits that form the building blocks of our digital world. Their story is one of constant innovation, from early scientific discoveries to the cutting-edge technology driving artificial intelligence and quantum computing. To appreciate the full impact of semiconductors, we must journey back to their humble beginnings and trace their evolution into the technological marvels we rely on today. The story of semiconductors begins with a simple observation about heat and electricity. In 1821, Thomas Johann Seebeck discovered the thermoelectric effect. A temperature difference across a conductor could generate an electrical current. This discovery laid the groundwork for semiconductor technology. In 1833, Michael Faraday found that silver sulfide's resistance decreased with temperature. These early seeds of knowledge would eventually blossom into the semiconductor revolution. The early 20th century saw significant progress in electronics with the invention of the vacuum tube. This bulky glass-enclosed device could amplify and switch electronic signals, paving the way for radios, televisions, and early computers. However, vacuum tubes had limitations. They were large, fragile, inefficient, and generated significant heat. The world needed a better solution, and it arrived with the invention of the transistor. In 1947, researchers at Bell Laboratories, William Shockley, John Bardeen, and Walter Brattain developed the first point-contact transistor. This revolutionary device, made from semiconductor materials like germanium, could perform the same functions as a vacuum tube but in a much smaller, more efficient package. The transistor marked a paradigm shift in electronics. It ushered in the era of miniaturization and paved the way for the complex integrated circuits that define modern technology. The transistor's impact on society was profound. It enabled the creation of portable radios, compact computers, and countless other electronic devices. It revolutionized communication, entertainment, and information processing. The invention of the transistor was a watershed moment in technological history, a testament to the power of scientific ingenuity and the transformative potential of semiconductors. The invention of the transistor was a major breakthrough, but it was only the beginning. As transistors became smaller and more efficient, engineers faced a new challenge: how to connect thousands, then millions of these tiny components. The answer came in 1958 with the invention of the integrated circuit, or IC. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed methods for combining multiple transistors, resistors, and capacitors on a single semiconductor substrate. This revolutionary concept, the integrated circuit, enabled unprecedented levels of miniaturization and complexity in electronic devices. It led to the development of the first microprocessors, the brains of modern computers. The integrated circuit, often called a microchip, became the foundation of the modern electronics industry. As manufacturing techniques advanced, engineers could fit more and more transistors on a single chip, following a trend known as Moore's Law. This exponential growth in transistor density fueled the rapid evolution of computers, leading to smaller, faster, and more affordable devices. The integrated circuit, a marvel of miniaturization and complexity, transformed the technological landscape and continues to drive innovation today. The creation of a semiconductor chip is a marvel of modern engineering. It involves a complex sequence of steps, each requiring specialized equipment and expertise. The process begins with silicon, found in sand and quartz. Pure silicon is extracted from silica rock. This silicon is melted and grown into single crystals called ingots. These ingots are sliced into thin wafers. The wafers undergo intricate processes. These include photolithography, etching, doping, and deposition. These steps build the transistors and interconnects forming the integrated circuit. The wafer is diced into individual chips. These chips are packaged, tested, and shipped worldwide. The entire process takes several months and requires precision and control. Semiconductor manufacturing highlights the industry's sophistication and technological prowess. The impact of semiconductors extends far beyond computers and smartphones. They are essential components in a vast array of industries, touching nearly every aspect of modern life. From telecommunications and automotive to healthcare and aerospace, semiconductors are the invisible engines driving innovation and progress. In telecommunications, semiconductors enable high-speed data transmission through fiber optic cables and wireless networks. They power the smartphones that keep us connected and the base stations that relay our signals. In the automotive industry, semiconductors control engine functions, manage safety systems, and enhance entertainment systems. As cars become increasingly autonomous, the reliance on sophisticated semiconductors will only grow. Healthcare relies heavily on semiconductors for medical imaging, patient monitoring, and drug delivery systems. From MRI machines to pacemakers, these devices rely on the precision and reliability of semiconductor technology. The aerospace industry depends on semiconductors for navigation, communication, and control systems in aircraft and spacecraft. The global reach of the semiconductor industry is undeniable. It is a testament to the transformative power of these tiny components and their ability to shape the future of countless industries. Despite its remarkable success, the semiconductor industry faces several significant challenges. The increasing complexity of chip design and manufacturing, coupled with geopolitical tensions and supply chain vulnerabilities, poses significant hurdles for continued innovation and growth. As transistors shrink to the size of a few nanometers, approaching the limits of physics, maintaining Moore's law's pace becomes increasingly difficult and expensive. New materials, architectures, and manufacturing techniques are needed to sustain the growth of computing power. The globalized nature of the semiconductor industry, while fostering innovation, also creates vulnerabilities. Disruptions in any part of the supply chain, from raw materials to manufacturing equipment, can have ripple effects throughout the industry. Geopolitical tensions, trade wars, and national security concerns add another layer of complexity. Semiconductors are now considered strategic assets, essential for economic competitiveness and military strength. Governments worldwide are investing heavily in domestic semiconductor production and research to reduce reliance on foreign suppliers and secure their technological future. The semiconductor industry, once driven primarily by market forces, is now navigating a complex landscape of technical challenges, geopolitical considerations, and national interests. The future of semiconductors is bright, driven by relentless innovation and the pursuit of ever smaller, faster, and more powerful devices. Researchers are exploring new frontiers, from quantum computing and neuromorphic computing to three-dimensional chip stacking. Quantum computing could revolutionize fields like medicine, material science, and artificial intelligence. Neuromorphic computing aims to create chips that process information like biological systems. Three-dimensional chip stacking increases density and performance while reducing the overall chip footprint. The industry is also focusing on sustainability, exploring new materials and recycling techniques to reduce environmental impact. These advancements highlight the dynamic nature of the semiconductor industry and its potential to shape the future of technology. From their humble beginnings in 19th-century laboratories to their ubiquitous presence in the 21st century, semiconductors have left an indelible mark on human civilization. These tiny giants of technology have powered the digital revolution, transformed industries, and continue to shape the world around us. As we stand at the cusp of new technological frontiers, the legacy of semiconductors is far from over. Quantum computing, artificial intelligence, and other transformative technologies rely on the continued advancement of semiconductor technology. The challenges are undeniable, but so is the ingenuity and determination of the scientists, engineers, and entrepreneurs pushing the boundaries of what's possible. As we look to the future, one thing is certain: the journey of the semiconductor is far from over. These tiny giants, born from scientific curiosity and nurtured by human ingenuity, will continue to shape the future, driving innovation and expanding the horizons of human potential for generations to come. Their story is a testament to the power of science and technology to transform our world and create a future limited only by our imagination.